Example 3. In this example, we're looking at a vertical spring hanging here, looks like at equilibrium, and suddenly you attach a fish to it. Hence, this kind of scale is called a fish scale. And it stretches this distance, which we'll simply call delta y. So we're asked in this problem to determine the spring constant k. Now we could graph it. That would be one way to do it, but that's okay. We're going to just go ahead and use our equation. Now, as you can see in the diagram, part of it's shown. We have the known information. So we were given that it was started at 10 centimeters or zero point 0.1 centimeters. And we put a negative in here because it's going down below. And then it's stretched to a new displacement of negative 0.124 meters. And the mass of the fish, this m right in here, is given as 4 kilograms. And we're trying to find the spring constant in part A. Okay, so there's a couple ways to approach it. Now, Hooke's law, if you want to use it in the true form, you could just simply write f sub x equals a negative k times x. Or you could write a delta x, right? Or in this case, since we're going in a vertical nature, you may want to replace delta x with delta y. So really you could say the spring force is equal to negative k times delta y. Okay, well we could find delta y right in here. Delta y is given as the final displacement minus the initial displacement, which would be negative 0.124 meters minus negative 0.100 meters. And that would give you a displacement of, well, negative 0.024 meters. So we're looking for the spring constant. We know delta y. What about, we're trying to find k. So we got to find that spring force. And there's a reason why there's a free body diagram drawn in here. You see, the fish is in equilibrium, which means that the sum of my forces vertically, hopefully you haven't forgotten forces, is equal to 0. It's not accelerating, right? It's at rest. So that means that the up force must be equal to the down force. The spring force must be equal to the weight, which I actually prefer to write as Fg instead of W. So F sub S minus F sub G must be equal to 0. So the spring force would be equal to the force of gravity. And if you recall, we can calculate the force of gravity by using just simply m times g. Right? And so F sub S would be equal to m, and mass of our fish is 4 kilograms times g, which is 9.8 newtons for every kilogram. That gives you a spring force of 39.2 newtons. So now we can replace it into this equation. The spring force is equal to negative k times delta y. We have 39.2 newtons equals negative k, and our displacement is negative 0.024 meters. And we get k is equal to 1,633 newtons per meter, which is rounded to 2 sig figs because there's only 2 sig figs with the mass. So you could say approximately 1,600 newtons per meter. So that's part A. And now part B is asking, well, what would happen if you were to suspend an 8-kilogram fish instead on the spring? So in part B, our new mass is now 8 kilograms. And we're now asked to find what will be the length of the spring in total. So we're trying to find out what y final would be equal to, right? So we know the initial y is, I assume, is a negative 0.1. That's when it's in equilibrium. And we have this m. So I assume that we could figure out the spring force again, the new spring force, which would be m times g. So that's going to be 8 kilograms times 9.8 newtons for every kilogram, which gives you a spring force of 78.4 newtons. And then we can set that spring force equal to negative k. And instead of delta y, I'm just going to write y final minus y initial. And we have 78.4 equals, well, let's make the assumption, hopefully you can say that, it's still the same spring. So the springiness, the spring constant, the stiffness of the spring is still going to be the same. So it's still 1,633 newtons per meter. And then we have our y final that we're looking for, and our y initial is negative 0.1 meters. So if we divide both sides by 1633 newtons per meter, we get, and this is, by the way, newtons over here, we will get y final plus 0.1 meters is equal to 0.048, and that would be in meters. And so hence, our y final would be equal to, oh, I made a little mistake here. It's not going to be 0.052, is it? Where did I make a mistake? Oh, the negative here. Well, that negative over here, let's just bring it over there, right? Right? Hopefully that makes sense. So it's going to be negative 0.048 meters minus 0.1 meters. So that will give you a final displacement of negative 0.148 meters, or negative 14.8 centimeters. And the reason why we have a negative here is simply because the spring, we're assuming this is 0, so it's 14.8 centimeters downwards. Okay, that's it.